Okay. So today we are going to begin with a new unit and a very interesting unit, biocoordination chemistry. Most important, bioinorganic or biocoordination chemistry. Just write a simple definition. It is study of coordination chemistry It is study of coordination chemistry at biological level. It is study of coordination chemistry at biological level. Okay. So coming to this, how many elements do you find in the periodic table? We find 118 elements, of which nearly 30 elements can be seen in the human life, human or any living organism. So nearly 30 elements we can see in living organisms. And if I just try to classify all these nearly 30 elements, I can classify into non-metals as well as metals. Okay. So can you just name one or two non-metals? Non-metals. These non-metals I can further classify into macro and micro. Macro means at a larger level, micro means at a smaller level. All these are macro non-metals: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur and chlorine. Micro non-metals: silicon, selenium, boron, fluorine and iodine. These come under non-metals at micro level, very, very smaller quantities. And when I come to metals, we classify them into macro, trace means small quantity, and ultra trace means very less quantity. Macro, trace and ultra trace. Macro means at a larger quantity, trace smaller quantity, ultra trace still smaller quantity. Okay. So any macro metals, then we have sodium, potassium, magnesium and calcium. They come under macro metals. Macro, the amount will be very less, but still within the metals we are calling them as macro. It means within the metals these will be in higher quantity. Trace elements: iron, copper and zinc. And for ultra trace, vanadium, chromium, manganese, cobalt, nickel, molybdenum, arsenic, lead and cadmium. Arsenic, lead and cadmium, they are not proper elements. They are not essential elements. These are poisonous elements, slowly which are coming into our body due to the intake. Whatever food that we are consuming, from that food slowly some elements are coming, such as arsenic, lead, cadmium and so on. Cadmium, you can find it in pigments, paints or in any other colors. Wherever you find some bright yellow color and all such things will be having cadmium in it. So whenever we consume or whenever we are very close to those paints, vapors will be coming. Slowly those vapors, you can smell it. Once you are smelling it means you are able to smell that chemical. Slowly it will be going into us, and that is how slowly cadmium may enter into our body. Tin, not tin, lead. How slowly lead comes? Lead pipes. Okay, lead pipes or some food which is completely packed in any lead containers. right? Such things, it will slowly seep into which that will come into our body. So we have to be very careful while taking these elements. Now slowly aluminum is also entering into our body. It is not an essential element, but aluminum is also entering into our body. Write down a point. Of all the elements present in living organisms, comma, metals play a major role. Metals play a major role. These metals are selected by nature. These metals are selected by nature for three different reasons. For three different reasons. These are metals have variable oxidation state. Variable oxidation state, comma, variable coordination number. Variable coordination number, variable means changing. Variable coordination number and variable coordination geometry. And variable coordination geometry. So when I am speaking of the metals, these are the metals which belong to transition elements, transition series. Because if I choose magnesium, or maybe I'll choose 1A group or 2A group elements, those 1A and 2A group elements will not have variable oxidation state. Previously I have given you some of the elements, sodium, potassium, magnesium, calcium. All those elements and metals, they have one common oxidation state, either +1 or +2 for calcium or sodium and etc. But if I choose iron, iron is present in hemoglobin, iron is also present in ferredoxins, it is also present in different metalloenzymes. So it can switch on its oxidation state from +2, it can go to +3. I choose copper, +1, +2. I choose zinc, but zinc anyway it is in +2 only. Zinc will be in +2. But there are several other metals which can switch on their oxidation state. Along with this, they can also switch on their coordination number. Switch on coordination number means, suppose if I am having a biomolecule, at the active site of biomolecule, the geometry might be tetrahedra. Tetrahedra means coordination number is 4. From that tetrahedra, slowly it will move to trigonal bipyramidal. One more ligand may come and attach. So from coordination number 4, it can go to coordination number 5. Sometimes it can even switch on to coordination number 6. So from 4 to 5 to 6, slowly it can switch on the coordination number. It can also switch on coordination geometry. Coordination geometry means, suppose that there is a copper enzyme. In that copper enzyme, copper could be present in +1, copper could be present in +2. For coordination number 4, copper 1 will prefer tetrahedral geometry. Copper 2 will prefer square plane geometry. So once there is a redox process, copper 1 to copper 2, geometry will also shift. It is possible only for transition elements. If I choose magnesium, sodium, calcium, all these things are not possible. So nature exclusively chooses transition elements to perform such functions for carrying the oxygen or metalloenzymes or electron transfer reactions. Mostly it will employ transition elements. But suppose to maintain osmotic potential, then it can go for potassium, sodium, so on. Just ions are important for it. They need not change its geometry, they need not change coordination number, but moving of ions is important. So it will choose sodium, potassium and so on. Magnesium is present. Where do you find magnesium? In chlorophyll. You can find it in chlorophyll. There it need not change its coordination number. It need not change its coordination geometry. Simply it has to exist as magnesium. Okay? So that is how the elements will be useful. Next point, what is the importance of concentration of a metal? Now I am not considering any non-metals. Our discussion is not non-metals. Our discussion is biocoordination chemistry. At biological level, I have to study the coordination chemistry where transition metals are involved. So I am not going towards the simple metals or non-metals. So concentration of metal versus physiological effect. When I say this, we have something called as essential element. What is an essential element? Essential element means, suppose if that element is present, I can survive, I can exist. But suppose if there is an element, even if I remove that element, I can still survive, nothing is happening to me. That is a non-essential element. Cadmium, non-essential element. It is just coming as an impurity. Lead, it is a non-essential element. Arsenic, it is not required for us. Non-essential element. So all these elements you can call them as non-essential. But essential elements, iron, it is essential. If I remove iron, person may die. Because hemoglobin does not carry oxygen in the absence of iron. Even iron deficiency is there, person will become anemic. So all those metals which I remove, it will create some physiological disorder. Such elements are called as essential elements. If I can supplement, again that physiological disorder will be removed. Suppose a person is anemic, so he is or she is iron deficient, I say. Now I slowly give some iron supplement. The physiological disorder is reversed. Then I say it is an essential element because it is present at some concentration. I am removing it, it is creating a disorder. I am again supplementing it, the disorder is being subsided or it is removed. Such element is called as essential element. Okay? So for such metals, if I check the physiological effect, then we have a simple curve. What type of curve is it? Just a bell-shaped curve. Okay? In this, a minimum concentration of metal is required for the survival of that living organism. Suppose if I want to survive, minimum amount of iron has to be present in my body. Minimum amount of copper or zinc has to be present. So that minimum concentration, because of which I am surviving, that concentration is called as concentration for survival. That is a minimum concentration. But I may survive, but I am deficient of something. You might have seen some people having legs which are crossed legs. Vitamin D deficiency will be coming in them. So due to that vitamin deficiency, legs will be becoming crossed. So that is called as presence of vitamin is there, but deficiency is there. It means the person is surviving, but that is not enough for the proper functioning. So that concentration where a person can survive, but deficiency is there. That concentration you are calling it as concentration of deficiency. They will survive, but they will have some physiological disorders. Then slowly I am increasing the metal concentration. So when I increase the metal concentration, I reach to a stage where there are no physiological disorders. I am absolutely normal. Nobody will call me as an abnormal. So that concentration where every metabolic activity is running at its best, that concentration we call it as optimal concentration, where every metabolic activity will be going on smoothly. Suppose I still increase concentration. It is just that if I take iron, it will carry oxygen into my blood. So if I consume more iron, then definitely that will affect my body. And that is, we call it as toxic levels. Slowly there will be some abnormal conditions or some diseases will be starting. And if I still start taking more, then finally the person may be dying also. So it will become so lethal that the person will die. So these are the various concentrations. What is the concentration required for the proper metabolic activity means optimal concentration. We call it as optimal. Optimal means that which is not high, not less, medium like. Okay. So you just take down this graph. You write a point. The importance of metals, the importance of metal concentration. the importance of metal concentration can be understood from the physiological functions it is involved in. From the physiological functions it is involved in. From the physiological functions it is involved in. Then you take down this graph. Some physiological functions, physiological effect, concentration of metal, lower to higher concentration, and these are some physiological effects. So this concentration, I am calling it as concentration of survival, concentration of deficiency, optimal concentration, toxic concentration, lethal. Toxic, lethal, they are interchangeable terms. But just to give its intensity, we are saying lethal means very dangerous. Who is selecting all these elements? Who is selecting all these elements? I am not choosing what element has to come into my body, but nature will be choosing. Nature will be choosing what element has to enter into a new life. So that is the reason we call nature as the biggest scientist. What element has to enter, which element should not enter, everything nature will take care of. You might have heard about some news also. Maybe if there are some hospitals, deliveries are going on, you might have heard. Now in these months, everywhere I hear about delivery of boys only. I am hearing about delivery of girls only. Have you heard about this? Everywhere I hear girl is born, a girl is born, girl, girl, girl. But sometimes you hear about boy, boy, boy. Everywhere you hear about boy. Have you heard or not? There also there is a power of nature. In science, there is a power of nature, because nature will be selecting whether a male should grow at a higher quantity or a female should grow at a higher quantity. There is a theory for it. So according to that theory only, sometimes male ratio will be high, sometimes female ratio will be high. Nature will be selecting it accordingly. Okay? Anyway, now coming to our biological chemistry. So as I told you, nature will be selecting. On what principles nature will be selecting these elements? What principles nature will be selecting these elements? There are 4 principles or rules. You may write down. Selection of different elements. Selection of different elements by nature selection of different elements by nature depends on 4 basic principles. Four basic principles. These are you can write down. First one, rule of abundance. If you go to a mobile shop, which mobile will you purchase? iPhone. Okay, you purchase iPhone. Why are you purchasing iPhone? Because just now I have produced Z phone or say X phone. Why are you not purchasing X phone? Because you have nowhere seen it. X phone or Y phone, you have nowhere seen it. Wherever that is abundant, okay, iPhone is present here, everywhere iPhone is present. It is not just available in Sri Lanka. You go to Pakistan, India, everywhere you go, iPhone is available. Therefore, you might purchase a iPhone. Just similar to iPhone, there is another phone, say M phone, X phone. Both can do the same functioning. Both are equally good. Then which one will you choose? This is available plentifully, this is also available plentifully. Then whichever can function more efficiently, definitely you will be choosing that mobile. Okay? So whichever is more abundant, first of all you will be choosing that brand. And of which, whichever is more abundant, whichever is more efficient. Suppose both mobiles are in abundant. This brand is abundant, second brand is also abundant. Then you will be checking which is more efficient. If this is more efficient iPhone, I will be choosing iPhone. Or if X phone is more efficient, you will be choosing X phone. Okay, efficiency is also done. Now I want to perform a particular function. I want camera to be the best. Mobile is abundant, it is also very efficient to perform, but I want to perform a particular function. I always want to take more selfies. Then I'll choose one type of mobile. Or I want to save data. I want to choose another type of mobile. Okay. Finally, I have a mobile, say Android 3 is present. Android 3, very old time, but just telling, Android 3 is present. Will you still switch on to Android 3? Every time you want your mobile to be updated, it will update on itself, but everyone wants to update from say 3G to 4G, now from 4G to 5G. You want to update. Why do you want to update? Why do you want to update? Because functioning has to be improved. So nature also does the same. We are part of nature, therefore we always mimic nature. We try to mimic the nature. So what does nature do? Suppose there are elements. How many elements are there? Nearly 90, 118, but transuranic elements are man-made elements. Out of these 90 elements, how many elements nature has chosen? Mostly 30. Out of these 30 elements, how many elements do you see below 30? Most of them are below 30. Hydrogen, carbon, nitrogen, oxygen, sulfur, phosphorus, sodium, potassium. Almost every element that we have seen is below 30. Why not it has chosen above 30 or above 40 or above 50? Mercury is not there, gold is not found, copper is not found to a greater quantity. Copper is there, but gold, mercury, silver, all those things are not found in me. What is the reason? Simple reason is rule of abundance. The first metals, earlier metals means 10, 20, 30, these metals, they are found in abundant. Their abundance will be high. So if at all nature want to prepare any human being or any living organism, the first rule it follows is rule of abundance. Whichever element is more abundant, that element will be chosen. Suppose I give you two elements which are both abundant. Then of these two elements, whichever is more efficient, that element will be chosen. Next one element is abundant, one element is efficient, but to perform a particular function, which element is needed? Nature will be choosing only that element. The remaining element, though it is abundant, though it is efficient, it will keep it away. And the fourth one, suppose if there is any improvement has to be done within the living organism, it will go on improving it. It is just like updating the software. This will also update. You might have seen how our faces used to be, how our head used to be. Head used to be this much large, thousands or millions of years ago. Now the head is coming shorter because that much brain is not needed now. We are doing more smart work. Therefore the size of the brain is also shrinking. Once the head was this much, now the head is coming small. Okay? So the same improvement is also done by the nature, that comes under evolutionary improvement of efficiency and specificity. Okay? So you just take down these principles. First one, rule of abundance. Rule of abundance. Nature chooses those elements that are found abundantly. Nature chooses those elements that are found abundantly. Okay. So here I am giving you an example. This will also come in the exams. What is that example? Zinc. Just say zinc is available in most of the enzymes. Most of the enzymes will have zinc at the active site. But if at all I take cobalt, I replace that zinc with cobalt. I am just replacing that zinc with cobalt. That same functioning can also be done by cobalt with same functioning with same efficiency, that function will be done by cobalt also. But nature has chosen zinc mostly. Why not cobalt? The reason is abundance. Zinc is more abundant than cobalt. But if I give you a function, that same function can also be performed by cobalt, but its abundance is less. Therefore, nature has chosen cobalt to a lesser extent. So scientists have done a simple experiment. What they have done is, they have taken such an enzyme, they have grown it in cobalt rich environment. Instead of zinc rich environment, they have grown it in a cobalt rich environment. Then that same action where zinc was performing, it was performed by cobalt with same efficiency. Only thing is, I have supplied more amount of cobalt. So zinc work can be done by which element? That can be a question. Zinc can interchangeably be done by cobalt. Okay. So if I grow an enzyme in a cobalt rich environment, the zinc functioning can be performed by cobalt also. You may write down that example. Zinc is found in several enzymes. Zinc is found in several enzymes. Several enzymes. Enzyme. Zinc is found in several enzymes. The functioning of these enzymes, the functioning of these enzymes can also be performed, the functioning of these enzymes can also be performed by cobalt. But since zinc is abundant, it was chosen. Zinc is abundant, it was chosen. Next, rule of efficiency. Rule of efficiency. Rule of efficiency. Can you name any electron carrier? Some proteins which can carry electron. Proteins that carry oxygen, hemoglobin, best example. Protein that carry electron, pyridoxines, cupridoxines, flavodoxines. All these come under electron carriers. So I am choosing flavodoxine, it is a non-metal electron carrier. I am choosing pyridoxine, it is a metal electron carrier or electron transferring proteins. Instead of saying carriers, I may call it as electron transfer proteins. Flavodoxine is an electron transfer protein. Pyridoxine is also electron transfer protein. Both are abundant. But which is more efficient? Nature will be choosing that. So out of flavodoxine and pyridoxine, pyridoxine is found to be more efficient electron transport protein. Therefore, nature has mostly chosen pyridoxine. Okay. So just write down that example. Rule of efficiency. Flavodoxines and pyridoxines are electron transport agents. Flavodoxines and pyridoxines are electron transport agents. Next, pyridoxines are more efficient. Pyridoxines are more efficient. Therefore, nature has mostly chosen. Nature has mostly chosen pyridoxines. Nature has mostly chosen pyridoxines. Okay. So whoever is more efficient, that person will be chosen for a particular job. In a similar way, nature also does the same. Third one, rule of basic fitness. I have chosen an abundant element, I have chosen an efficient element, but to perform a particular function, which element should I choose? Is given by rule of basic fitness. So what is the example given? You might have seen some animals where there will be protective covering for it. Protective covering usually made up of calcium carbonate, shell. You call it as a shell. So most of the shells that you find, there will be a small creature in it. That creature will be creating that shell so that it will be protecting it. But there are some small organisms called as diatoms. We are calling them as diatoms. For these diatoms, instead of calcium carbonate as a protective covering, it has made silica as a protective covering. What could be the reason for it? Calcium carbonate is an efficient covering. Silica is also an efficient covering, but mostly you find calcium carbonate. Calcium carbonate is transparent or opaque. It is opaque. Light will not travel through that calcium carbonate shell. But if I take a silica, silica is like sand crystal. Silica is nothing but like a sand. So with that silica, if there is a very thin layer of protection, light can also travel through it. So diatoms will protect themselves not with calcium carbonate shells but with silica shells. The simple reason is light can fall through it and it will prepare its own food material, process of photosynthesis. But if it is preparing with calcium carbonate, that functioning will not be done. The organism may die. So there is a function called as protection which can be done by calcium carbonate. This is abundant. Silica is also abundant. This is efficient. This is also efficient. But to carry out a particular function, nature has chosen only silica for diatoms. That comes under rule of basic fitness. Okay? Write down that example. Of OF, of the abundant and efficient elements, OF, of the abundant and efficient elements, of the abundant and efficient elements, comma, the one required for a particular function, the one required for a particular function is selectively chosen by the nature. Is selectively chosen by the nature. Example, calcium carbonate and silica, calcium carbonate and silica can form protective shells. Calcium carbonate and silica can form protective shells. But diatoms prepare the shell with silica. Diatoms prepare the shell with silica, which could be due to its transparency, which could be due to its transparency to carry out the process of photosynthesis. To carry out the process of photosynthesis. To carry out the process of photosynthesis. Okay, last one. Evolutionary improvement of efficiency and specificity. Evolutionary improvement of efficiency and specificity. Evolutionary improvement of efficiency and specificity. It means how you are updating your software. Similarly, this also doing it. Copper 1 convenient with tetrahedral geometry for coordination number 4. Copper 2 is convenient for square plane geometry. But at active site, suppose there has to be a switch on between the two geometries. One is tetrahedra, another one is a square plane. The energy variation will be very high. Every time from tetrahedra, suddenly I want to go to square plane, there is a lot of energy change. Square plane will be having more energy involved in it. Okay? Tetrahedra, lesser energy, because square plane is generally found to be more stable with a greater CFSC. Tetrahedra has a lesser CFSC. So energy difference will be very high between these two. What nature has done is, instead of fixing itself into a perfect tetrahedra at an active site, it has done itself into a distorted tetrahedra. Why it is a distorted tetrahedra? Suppose if this is a perfect tetrahedra, okay, if this is a perfect tetrahedra, from here if it has to move to square plane, lot of energy is needed. But instead of a perfect tetrahedra, suppose if it is almost like a square plane, it is like a distorted tetrahedra, then to move into square plane it requires lesser energy. So nature is improving itself so that from moving from a tetrahedra to square plane, if more energy is needed, it is not fixing itself into a perfect tetrahedra, it always fixes itself into a distorted tetrahedra so that it can easily transfer into square plane. This is called as evolutionary improvement. Okay, you can just write down that example. For coordination number 4, copper 1 prefers tetrahedral geometry. Copper 1 prefers tetrahedral geometry, whereas copper 2 prefer square plane geometry. Copper 2 prefers square plane geometry. Next point. The switching on means moving from one geometry into another geometry. The switching on geometries require greater energy. Switching on geometries require greater energy. Hence it is always seen, SEEN, it is always seen that the active site contain distorted geometry. The active site contain distorted geometry. In bracket you put it as entactic effect. Entactic effect. It is a biological term. It is not needed, but just you have an idea. Entactic effect. Entactic effect. Okay. So if you want, you can roughly draw. This is a perfect tetrahedra, supposingly. This will go on with some distortion so that it is very much closer to a square plane, and transition becomes easier. From a distorted tetrahedra into a square plane, energy required will be less. Finished? Write down a point. Biocoordination chemistry can be easily studied under three headings. These are oxygen binding proteins, electron transfer proteins, and metalloenzymes. Oxygen binding proteins, electron transfer proteins, and metalloenzymes. Next point. Write down. The metal is generally surrounded by The metal is generally surrounded by ligand environment. Ligand environment. Ligand environment. There are different types of ligands. There are different types of ligands. Some of them are called as macrocycles. Some of them are called as macrocycles. Macrocycles. The most commonly found macrocycles, the most commonly found macrocycles in living organisms, the most commonly found macrocycles in living organisms are first porphyrin, CHLORIN, CORRIN, and CORPHIN. CORRIN and CORPHIN. You may just draw these structures. Structure will be little larger because it is a macrocycle. So you may draw accordingly. I am drawing in the most easiest way. You may just follow this, or if you have any other easy method you can follow. First just draw 4 5-membered rings, spiral rings. For all of these macrocycles, 1, 2, 3, 4, altogether 4 5-membered spiral rings. I am drawing it like a square plane relation between the 4 nitrogens. So once that is completed, then we will be joining them with methane bridges. We call it as methane CH2 bridges. The most important one is the first one, porphin. You can even count the number of double bonds. There is a change in the number of double bonds. First one, how many double bonds? You may just start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What difference do you find? Only 10 number. So here there is a double bond. I have not drawn it here. So there are only 10 double bonds in conjugation, 11 double bonds in conjugation. Next, how many methane bridges? 1, 2, 3, 4. How many? Only 3. 1, 2, 3. This is not a methane bridge. A very, very important point for CORRIN. What do you call it as? Cyanocobalamin or cyanocobalamin? Not cyanocobalamin, it is cyanocobalamin. Cyanocobalamine. Vitamin B12 will be having that ring. And the most important point is there are only 3 methane bridges. So don't put a CH there. And in the last CORPHIN, it is also called as hydrocorphin. Nickel can be found. We call it as MCMR as an example. MCMR. Methyl coenzyme M reductase, where nickel is found. Methyl coenzyme M reductase. Vitamin B12 coenzyme. Chlorophyll. Hemoglobin or myoglobin. So where do you find porphine macrocycle? Answer is you can find it in hemoglobin or myoglobin. This is not a porphyrin. Please remember, this is a porphine macrocycle. When I say porphyrin, there are some substitutions. There will be some substitutions. Without any substitution, this is a basic ring that I am giving you. This is called as a porphine. When I draw porphyrin, then you have to put substitutions. Okay? Next, chlorophyll will be having magnesium at the active site. Magnesium will be present at the active site. If you want, I am just drawing that also. I am taking iron as an example. In this case, I am taking magnesium at the active site, cobalt at the active site, nickel at the active site. Only one hydrogen, two hydrogens, two hydrogens. So all these points you have to note down. You may also write down the number of double bonds. 11, 10. How many double bonds? 6 and then 5. 11, 10, 6 and 5. Which is called as workhorse macrocycle. Who is a workhorse? The person who works a lot. Suppose there is any organization or a pharma company or something else, a person will be working to a greater extent. Such person is called as a workhorse. Workhorse is called as porphine, because most of the biological proteins you can find porphine in comparison with chlorine, not chlorine, Ne will not come, simply N. Chlorine, CORRIN or CORPHIN, this is found to be in a higher quantity. Okay, therefore this is called as workhorse macrocycle. Porphine is called as workhorse macrocycle. Which is called as workhorse in chromatography. Different types of chromatographies are there. Gas chromatography, HPLC, column, so on. TLC is called as workhorse chromatography. TLC, thin layer chromatography, because it is used to the greatest extent. TLC, that will come in chromatography anyway. Finished? Okay, the last one you write it as MCMR. MCMR means methyl coenzyme M reductase. Methyl coenzyme M reductase. Methyl coenzyme M reductase, where you find nickel at the active site. It is actually not planar, it is puckered. If all there are double bonds and in conjugation, then the ring will be planar, but this is non-planar. It is a puckered ring. On board it looks like a planar one, but it is not a planar macrocycle. MCMR, methyl coenzyme M reductase. put the heading as oxygen binding proteins. Oxygen binding proteins. Oxygen binding proteins. You have this in your syllabus. Very important topic. No question paper without these questions. Write a point. These are the proteins. These are the proteins where oxygen binds, reversibly at ambient temperature and optimal partial pressure of dioxygen. At ambient temperature and optimal partial pressure of dioxygen. Dioxygen means O2. O2 as a ligand we call it as dioxygen. Optimal partial pressure of dioxygen. Right. So what is the most important terminology that we have used is reversibly. Because iron you might have seen rusting. Iron will be rusting wherever you just keep it exposed to moisture. Once there is no moisture, no rusting. But there is some moisture even in the atmosphere, rusting happen. That is called as a irreversible bonding. Iron oxides will be formed. It is irreversible. It is not that it has formed iron oxide, again oxygen is given, again iron. It is not so. It is irreversible. But within the living organism, whenever oxygen is binding to a protein, we call such a binding as reversibly. Reversibly means protein will combine with oxygen, will form a complex at one particular partial pressure. Once that partial pressure of dioxygen drops, the reaction will be reversible. Okay? So suppose I am inhaling, at the lungs the partial pressure of oxygen will be very high because I am inhaling the air. So at a very high partial pressure of dioxygen, the hemoglobin protein will bind to oxygen. It will form a complex, and that complex will be taken to the tissue or the cellular level. At cellular level, the partial pressure of oxygen will drop because I am inhaling, the lungs will be taking up the dioxygen, partial pressure is high, but at tissue or cellular level, the partial pressure of dioxygen is low. Since the partial pressure of dioxygen is low, this complex cannot survive. It will give away oxygen, again it will come back to protein plus oxygen. Oxygen is given away, protein will again come back through the blood, take up dioxygen. This process is continuous. Such a type of bonding is called as reversible bonding, and it should not be very strong. The bonding between the protein and the dioxygen should not be very strong. It should not be like iron and cyanide. Mostly iron and cyanide, it will form a very strong bond. You might have heard about cyanide poisoning. Even if I take a little amount of cyanide, immediately poison, we call it as cyanide poisoning because iron binds to cyanide so strongly, it will not come out. Very, very difficult to come out because cyanide is a pi acceptor. Sigma donor and a pi acceptor it is. Okay? So multiple bonding will be there, bond will be strong. But when it comes to dioxygen, dioxygen is non-polar. It is non-polar. Therefore bonding is not strong. It is a weak bond, and that bonding is reversible. At one partial pressure, it will be binding. At another partial pressure, lower pressure, it will be unbinding. Even if temperature increases, it will be reversible. As temperature increases, this process will be reversible. And if there is less amount of oxygen present, we feel less energetic because oxygen is used for what process? Respiration. If there is no oxygen, I cannot respire, no energy will come. If there is oxygen, process of respiration will occur, energy will come. So whenever I get a fever, I feel very lethargic because oxygen will not be coming properly. Temperature is high. So that is the reason you have to drop the temperature for normal metabolic activity. Okay. Before going into dioxygen, you just write a few points. O2 is thermodynamically very reactive. O2 is thermodynamically very reactive because it is a spin triplet. Because it is a spin triplet. It is a spin triplet. But in living organisms, it reacts slowly. In living organisms, it reacts slowly because most of the organic molecules are spin singlets. Most of the organic molecules are spin singlets. Spin singlets means there will be no unpaired electrons. Usually if I choose any organic molecule, do you find any unpaired electrons? No. Glucose, no unpaired electron, right? But suppose if at all I am choosing dioxygen will have two unpaired electrons. So we call it as a spin triplet. It is highly reactive. But if at all that oxygen enters into my body, it will not react with my body so easily because my body contains organic content. That organic content is spin singlet. There are no unpaired electrons in it. So once it is entering into body, its reaction will be very slow. It will not react. If it is a radical, it will react. If it is a radical. But simple dioxygen reaction will be very, very slow. We call it as sluggish. Sluggish means it is very, very slow to react. The simple reason, it is a triplet, but our body will contain organic molecules which are singlets, no unpaired electrons. Then put a subheading, bonding modes of dioxygen. Many times questions appear just from this topic. You may go through any question paper related to national or state level exam. Just a look and then you can write it. If I am drawing a simple dioxygen, every time I need not put a double bond because as a ligand I am representing it as O bond O. You can understand every time I need not put a double bond. These ones are called as end. This is an end. This is an end. So this particular side is called as an end. This one is called as a side. This is another side. This is an edge. This is an edge. Side, side, edge, end, end. Okay. So if at all a metal is coming and if it is binding at this point, we call it as end-on bonding mode. It is end-on because it is binding at end. Again in that end-on, if only one metal is binding, we call it as end-on terminal bonding mode. This is end-on terminal. If there is another metal, you call it as end-on because it is binding here, but it is bridging. End-on terminal, end-on bridging. This is edge-on. It is exactly the edge. This one is side-on. Side-on terminal, side-on bridging. Dioxygen is present between the two metals. Where do you find this type of bonding mode? Hemocyanin. you have only 3 oxygen binding proteins: hemoglobin, hemerythrin, hemocyanin. In hemocyanin, you will be finding this. In hemoglobin or myoglobin or hemerythrin. So terminal bonding mode is very important. The two end on terminal. In hemoglobin you can find myoglobin, you can find hemerythrin, myohemerythrin, but in hemocyanin you will be finding side on bridging. Everywhere we just show as a single bond only, but bond order will be changing according to the metal that it is binding with. In some exams, they are also giving you, have you taken this example, hemoglobin, myoglobin, hemerythrin. You simply write it as HB, MB, HR. This is called as neta 1. Neta 1 means with respect to the ligand, it is called as monohapto. This is called as monohapto. Haptene means to bind or to fasten. So this particular ligand is binding with how many atoms is given by hapticity, neta. It is binding with only one donor atom, therefore neta 1. In this case, this particular ligand is binding with one donor atom to one metal, second donor atom to second metal. I call it as neta 1, neta 1. This is neta 1, this is also neta 1. Suppose I come here, this is like neta 2. Both oxygens are bound with one metal. This is also neta 2. This one, these two oxygens, neta 2 to one metal. Again these two oxygens are also given to the another metal. You call it as neta 2, neta 2. That was a previous CSR exam question. So neta 1, neta 1, neta 1, neta means hapticity, where how many donor atoms of the ligand are bound with the metal. That is called as hapticity. Okay. So in this case only one donor atom, neta 1, only one donor atom, neta 1, neta 1. In this case both oxygens are bound with the metal, but you call it as a edge on bonding mode. The bonding is very weak and very rarely you find such a bonding. So neta 2. Next one is also neta 2, but it is strongly bound. This one is little bit stronger. Last one, it is neta 2 and neta 2, where you can find it in hemocyanin. Best example is hemocyanin. Finished? End on, edge on and side on, remember. You can write down this last table. You may call it as dioxygen or dioxo. Dioxygen or dioxo. Superoxo, peroxo. What is N? Number of unpaired electrons. I am taking 3 different species, I am calling them as O2, O2 minus and O2 2 minus. Dioxygen or dioxo, superoxo, peroxo. Generally dioxo is a terminology where we use 2 different oxygens present. So that might be confusing. For that reason we generally use dioxygen. But in some terminology it is also called as dioxo. But in coordination chemistry when I say dioxo, this can also be a meaning, 2 oxygens. So be careful in that terminology. Number of electrons 16, 17 and 18. Number of unpaired electrons is 2, 1 and 0. This is stretching frequency of dioxygen. Very, very important data. You have to blindly remember 1,555 for dioxygen. If it is a metal superoxo or metal peroxo, depending on the metal it will be from 1100 to 1150. So depending on the metal, which metal is combining with it, there will be a range. But for simple dioxygen it is 1,555. For metal dioxygen it can range from 1100 to 1150. And for metal peroxo it will range from 800 to 900. What is the thing that you are finding now? Stretching frequency of dioxygen is decreasing. Why is the stretching frequency decreasing? Because the number of antibonding electrons are increasing. These are antibonding electrons. Okay? So there are 2 antibonding electrons. I mean 2 in the sense, I am speaking about the 2 pi. 2, 3, 4. The number of antibonding electrons are increasing. Bond order decreases. As bond order decreases, stretching frequency also decreases. As stretching frequency decreases, bond length increases. You can see bond length 1.2 angstroms, 1.24 to 1.31. Here it is nearly 1.3 to 1.5. So the bond length is increasing. For angstrom A0, this is the right one, not this one. In exam the questions will appear in this way. There is an oxygen binding protein. For that oxygen binding protein, the stretching frequency was seen to be around 1100. What is the type of bonding mode? Then based on that you have to give the answer. Anywhere around 1100 it has to be superoxo. Anywhere around 800, 850, 900, or even it could be 750. In some rare cases it will be below 800 also. It is peroxo. If it is anywhere around 1500, it has to be dioxo only. Okay? So that is how we confirm. Today we'll just stop with this. Later on we'll be beginning with porphyrin in the next class. But before going into the next class, just a small finding. You can see this in anywhere in the science articles also. Even in the internet it is available. How many times do we breathe a minute? Fast. How many times do we breathe a minute? 72 times or 70 times? 72. How many times do we breathe a minute? 72. Sure? Not sure. 70 to 80. How many? Be louder, no problem. 72. (12 to 16). Where is this coming from? Where is 70? Where is 16? I did not ask you heartbeat. I have asked you breathing. How many times do we breathe a minute? So 12 to 16 is the right one. But who is breathing 12 times a minute? Now no one is breathing 12 times a minute. At least 20 to 30 years ago, the number of breaths that we used to breathe, average was 15. Average was 15. Now it has increased to 17. The average number of breaths has increased to 17. they have found a relation between the number of breaths and the lifespan. You can just go through the data also, you will be finding. If at all you take a giant tortoise will be breathing 4 times a minute. It will just breathe only 4 times a minute, hardly 2 to 4 times. In this 2 to 4 times, it can survive up to 150 years. It can survive up to 150 years. A horse which can breathe from 15 to 20 times, it will anywhere not 70, maybe 60 years I guess. But a dog which breathes 30 times a minute, it can hardly survive for 20 to 25 years. And you might have seen a mouse. It will be anywhere around 150 times a minute. It will breathe for 150 times a minute. And hardly it will survive for 1 year only. It can hardly survive for 1 year, a simple mouse. Because its breathing rate will be anywhere from 100 to 150. So fast it will breathe, so fast it will die. So what is the final conclusion from this table? The more faster we breathe, the more faster we die. And that is what it was seen in all the animals. They have not just given this data. If you open the internet, you can find shrew, mouse, monkeys, horses, elephant, dog. All these animals are given how many times they breathe a minute and what is their lifespan. Everything has been related. Previously, before 10 or 20 years ago, the number of stress levels were very low. So the number of breaths, it were anywhere around 15 on an average. Sometimes if I do an exercise, it will go to 25 or 30. But when I don't do any exercise, if I'm very calm, it will be maybe 10 or 12. So the average was 15. But now the stress levels have increased. Everything is now very fast. So my breaths have also increased. And proportionately, lifespan has decreased. But indirectly, we are increasing our lifespan through medicine. It is not that our lifespan is increased to 70. It is only due to medicine that we are increasing it, or else the average lifespan is decreasing by the number of breaths. So they say that everything you do it slowly and calmly. If you have more stress, more cortisol will be released, more breathing, you will die fast. Okay? So be careful while breathing. We'll continue in the next class.